So welcome to a new video in the video series on systems biology, digital twins, and AI. This video series is a part of the material in TBMT42 block 1, but it's also generated to be used in various other research networks such as Stratify and Excite. So what we'll talk about in this particular video is Hodgkin and Huxley type of models. And they appear in electrically active cells, in particular neuron-like cells or beta cells or that type of cells. So for instance, they appear in brain models when you look inside a part of the brain and you create these neuronal networks. Then each cell here is described by a Hodgkin Huxley type of models. And what we'll talk about in this video is simply how to go from this type of electrical circuit description of a model to a state space form, ordinary differential equation form. Okay, let's dive in. And let's change the pointer to laser pointer. Okay, fine. Hodgkin and Huxley. You see here, Hodgkin and Huxley. They published a series of papers in the early 1950s, and which characterized, first experimentally, the electrophysiological properties of a giant squid axon. So they looked at a single nerve and characterized the electrophysiological properties of that. And a key aspect of that, a key aspect of the big breakthrough, was that they combined these type of experimental characterizations and the parameters that they could determine into an ordinary differential equation model, which they then were able to simulate to get a good agreement with data. And the idea here was that they could use the analogy of that it functions essentially as an electric circuit, which we already have the equations for. So all the simulations at that time was very, very, very time consuming. So you actually had a physical device that you manually had to turn like this for each step in the simulation that you learn about in some other videos. So each step in the simulation, which now is done very, very fast by computers, they had to do this by hand. It was a physical device that did it. So they had to stay up all night just to do a single simulation. But even though they had this very rudimentary access to the ability to simulate, already from the start, they had a very impressive agreement with the data when they put all of the components together. And the model has been a cornerstone for electrophysiology ever since, so for the last 70 plus years. And this model was published in 52 in Journal of Physiology, and they received the Nobel Prize in Physiology and Medicine in 1963. So now let's look at this diagram here. So we have some different components, as you see here. So let's go through them one by one. Let's start with the symbol here to the left, which is a capacitor. And this capacity, the ability to sort of have two layers and opposing charges on the two different sides, is simply a property of a lipid bilayer, so the membrane of the cell. And this is simply the basic equation for a capacitor. It's basically the definition of capacitance. And the key observation here is that here we have dV dt. So this is sort of the origin of a differential equation, the one for the voltage. And it says how the time dependency or the time derivative of the voltage is related to the current. And this relation is simply given by the capacitance. Okay, so the other components here have to do with the ion channels. So ion channels wasn't really conceptualized in the way that we think about it today back then, but they could change the ion concentrations outside the cell, and they could characterize sort of parameters that had to do with what we now understand as an ion channel. And it simply consists of the ability to transport ions through the membrane. And each of these ions have their own resting potential or reversal potential, which is the membrane potential where there is no net flux of those ions. And this is different for each ion. And if you're away from that, so if the membrane potential minus this reversal potential is non-zero, you have a voltage across that particular opening. And then you have a resistance. So you sort of have a sort of battery, which is this potential difference, and then you have a current through. And as with any current through something, there is a resistance, or the inverse of the resistance is a conductance, the ability to lead through ions. And this conductance is given by G, and this is simply Ohm's law. So this is the voltage, and this is the current, and this is the conductance. So this conductance here is then specific to each ion channel, and this is what will lead to the other differential equations. But let's, before we turn to those, let's just sum up these components here. So we have this current here, and we have these currents here, and they simply add up. So we just add them together, and then we have the total current. And if you want to create a standard form of a differential equation, then you simply move this to the left-hand side and you divide by Cm. So this is the first differential equation. So now let's look at these G's, these conductances. And they are broken down into a maximal conductance and a degree of openness, which is a value that lies between 0 and 1. If you're at 1, then you are, of course, at the maximum capacity. So you multiply these values together. And this openness is a probability which depends on if the channel is open or closed. So you have here a probability of a channel, or actually a subunit of a channel, being open and it's being closed. And the transition rate constant here is alpha and beta in two directions. And since these are two probabilities and they are the only two states that they can be in, they sum up to 1. And because of that, mathematically, we can rewrite this so that we only have one of those that we can call n, which is here the probability of it being open. And then the probability of it being closed is simply 1 minus n. So mathematically, this is identical, but this is maybe the more normal way from a biochemical point of view to write it. And we already had a video on how to go from these type of reactions to ordinary differential equations. So it's simply this state, 1 minus n times alpha for this direction. And for the other direction, it's this state times beta. And if we look at the differential equation for this one, then it's a plus sign here because it's going in this direction, and a minus sign here. So these are the other differential equations, and you have one of these for each ion channel. And here, these alphas and betas, they in turn depend on the voltages. And this is why you have the crosstalk. This is why you have all of the complicated dynamics, because you have this crosstalk between the voltage and the probability transitions between closed and open for the channels. So these alphas and the betas, they depend on the voltage. And here, these are parameters 0.01 and 10 and so on in the fairly phenomenological expression, especially back then, for how these dependencies on the voltage can be described. So they could experimentally characterize them by changing the voltage in voltage clamp experiments, and then they could characterize these type of properties of the different ion channels. Okay, so the final thing to know, to be able to put all of this together, is that these transitions in the early phases was just for a single subunit of an ion channel. They didn't really understand those mechanistic details because the ion channel wasn't characterized, but that's how we understand it today, that there are different subunits to a channel. And if they are identical and they are independent, then these are simply probabilities that are multiplied with each other. So the full probability of it being fully open, which is the state that is actually sort of active. The other ones are intermediary states. So the fully open state, the probability of being in that state where all 4 subunits are open, is simply n to the power of 4. So these equations are the differential equations with these auxiliary equations for the ion channels, and we are ready to put all of this together. So this was the one from the first slide, adding all of the currents together, and these are these reaction-based transitions, where again, remember that the connection between here the voltage differential equation and the openness probabilities is the fact that these transition rate constants, which often in other type of biochemical models are simply constants, here they are governed by the voltage. So that's the connection, and this is a nonlinear connection, and this is what gives rise to all of this complicated dynamics that they can produce. So they put all of this together and they simulated curves that we see here, and these are experimental data of these voltages for an action potential. So you see the agreement between the data and simulation are very good, and they can also look at the individual variables. So here we have the voltage across the membrane, and here we have these conductances for the sodium channel and for the potassium channel. So the rise here from very negative, -70, something like this, millivolts, up to maybe +30. That's called the depolarization phase, which is driven by the opening of the sodium channels. And then we have the repolarization back to negative values again, which is caused by the closing of the sodium channels, which we see here, and the opening of the potassium channels, which we see here. So you see that they have slightly different dynamics. And in the end here, we have a hyperpolarization before it goes back to the original baseline. And in practice, often you have series of these type of action potential in bursts. And we'll return to more details of how to understand these type of oscillations mathematically in the videos that we have also in block 1 on bifurcations and nonlinear dynamics. So just to wrap things up, let's look a little bit forward. So we talked about what happened basically in the early 50s, 70 years ago. Let's see what has happened since. So a key step forward was Frankenhäuser 10 years later, published also a series of papers in Journal of Physiology, characterizing corresponding properties in vertebrates, in frogs, for instance. And then he saw that basically the same ideas holds, but that there are some nuances in terms of the detailed properties of these ion channels. And these type of models are now used in roughly the same form as they were originally in large neuronal network models that are simulated in packages such as neuron. But of course, since then, a wide variety of new types of data and knowledge have appeared. So one of the most important of those is gating currents, which is not the current that is caused by the ions going through the channel, but by these reconfigurations within the channel, the movement of the subunits, which are charged particles. So you can actually measure the currents that are produced by the movement of charges within the ion channel. So this is called gating currents, and this and many other things has allowed us to find out much more details about the exact transitions and properties within the ion channels. So nowadays, a current state-of-the-art description of the opening and closing of, for instance, a sodium channel looks maybe something like this. So here we have the different subunits, and here we see one transition for one of these subunits. Here from an R to P and so on, and here we have separate steps in the end for the actual opening of the channel, and then for the inactivation of them and so on. So we can nowadays characterize the paths that the channels goes through in different ways here. So we have this much more detailed understanding of the individual ion channels and their internal dynamics nowadays. So this particular model is part of a paper that we hopefully will publish soon. So Nicholas Sundqvist here is the first author. He's also a supervisor in the course, and the main expert who has worked with these type of models and experiments for many decades is Fredrik Elinder. He will be the last author of this paper. So if you want to know more about these type of models, and if you want to do an individual project in this direction, you should talk to one of these guys. Okay, that was it for the Hodgkin and Huxley type of models.